Hi, everyone. Thanks for joining the AI at Scale Yuan today. This is the second live QA session. My name is Michael Zhang. I'm the engineering manager at Meta AI Infra, and I will be a host for this QA session. I hope you have enjoyed the presentations and are excited to, as I am, to hear from our presenters to answer some of the really interesting questions. Before that, let's first start with a very quick roundtable introductions. Yuan, can you introduce?
Hi, this is Yuan. I'm a technical fellow at Microsoft. I lead the Microsoft's AI frameworks team, and the team is responsible for how to efficiently train very large models and how we can infuse AI everywhere in every platform, application, and products.
Great, thanks, Yuan. Sujoy?
Hi, I'm Sujoy. I'm the head of computer vision and applied machine learning research here at Unity, where we have a real interest in understanding the ways in which synthetic data can help improve models in the real world, their production quality in the real world.
Great, thanks, Sujoy. Jake?
Yeah, hi, I'm Jake Mannix. I'm a principal architect for Search and AI at Salesforce, where we try to get kind of AI-infused intelligence into kind of all of the kind of business intelligence that Salesforce produces.
Awesome, thanks, Jake. Next up, Krishna.
Hey everyone, I'm Krishna Gade. I'm the founder CEO of Fiddler.ai. We are a model performance monitoring startup in Palo Alto.
Awesome, thank you, Krishna. Next.
Yeah, hi, I'm Peng Wu. I'm the engineering manager supporting PyTorch compiler. Everybody knows about PyTorch, and compiler is trying to improve the efficiency and the scaling of PyTorch.
Great, thank you, Peng. Last but definitely not the least, Andrea.
Hi, I'm Andrea. I'm the chief engineer for AWS SageMaker. SageMaker is our ML platform at scale that you can use to build, train, and deploy your models on AWS.
Awesome, thanks, Andrea. Great. So without further ado, let's jump into the QA. We're gonna start with a couple of kind of general questions. So the first question is for Yuan and Sujoy. So what does scale mean for you, and why it is important for companies to think about scale very early on?
This is a very good question. So it's a question I've been dealing with for the past few years. And so for me, the scaling means several things. And as you know, the model is getting really, really big, and also it's producing amazing results. And how can we efficiently or effectively train this kind of models? And it's becoming a big problem. And so training is only part of this problem. And so once we train the models, when we have to cost effectively serve the model. And so that is, to me, is where the problem is at this moment. As the model is being trained is amazing, but how we can save it without losing money. And so that's becoming a very, very important. And so the third dimension of it is what I call the infuse AI everywhere. So that's another scale. It's to scale it out across all the platforms, all the applications, and every product. And so in the context of Microsoft, we have Office. There are many Office applications, and the Skype, and the Teams, and the Office docs, the PowerPoint. Every place we like to have the AI infused, but the AI model has to run seamlessly in the application context in the environment. So that's actually is a very, very, very big problem. And so I'll probably stop here, but so that's the my definition of the scale and that all the problems my team has been dealing with.
Thank you, Yuan. Great point. Sujoy, anything you want to add?
Yeah, no, it's great point, absolutely, and I agree, with it. I think for me, the way I've always framed this question as it sort of starts with the data. It is the scale of data you want to use for training. It's the scale of data you want to consume at inference. Because of the scale of data, particularly used at training, the model scale gets larger and larger, making it harder and harder to think about how to do the inference. And this is actually one of the reasons I think it's so important to think about this early as an organization or a company, is that establishing a scalable data strategy, and then a scalable model serving strategy, and then a scalable model monitoring strategy is going to be critical for you to be able to hit those types of scale of models that perform at better and better quality, are more and more integrated with more and more of your services, and are able to be managed as they proliferate in your company. And I think if you don't think about those things early, you don't have to have all the answers early, but if you don't think about them early, I think you can get into a real problem very quickly.
Great, thank you, Sujoy. I think we can all agree, AI scale is super important and area, and that's partly why we are here today. Second question, as we talk about grow AI scale, what are the things that we should watch that will be the next bottlenecks? I think the question are for Krishna and Jake. Maybe Krishna, if you get started.
Yeah, so I think people talked about scaling data and the systems around models, right? I think once you get enough models into production, one of the things that you will run into is lack of visibility into how the models are performing, and that would basically hinder in terms of how many models you actually would be able to put into production safely, and how do you make sure that they are still affecting the business in the optimal way. So model monitoring, cost performance issues will become very important, and we have seen this in other spaces as well, right? When a decade ago, when teams were building lots and lots of software services like microservices applications, the need for observability became really huge. And Jake and I were at Twitter together, and we faced that problem. We didn't have any observability tools and had to build our own. So what we are seeing is teams are facing similar issues now with lack of visibility as they put more and more models into production. So that's one thing one needs to care about.
Absolutely. I think model monitoring is definitely super important. Jake, anything you want to add?
Yeah, it's interesting actually when you harken back to the problems of proliferation of microservices. It's exactly the thing I end up thinking about when it comes to next bottleneck of scale is not necessarily just on the scale of individual models. People think about AI applications as being like a big model that you have with some features fed in and you get something out. But really, that's just one tiny little endpoint. An AI application tends to have a bunch of stuff stitched together. It does many different things. It may consult databases. It may consult a feature store. It may feed into another model. It may federate out to 3 different things and ensemble them together. The scaling that will start to get to be complex is not just the number of models you have in production, but now the web of stuff in between all of them, and how to actually maintain all those connections and kind of have them interoperate sensibly. That's going to be extraordinarily complex. And you can already see it, especially in kind of search and recommender spaces, as well as chatbots. They get to be extraordinarily complex systems. Just like any software project will get to be a big complex system as it scales out. AI is going to start entering that space. If it hasn't already hit you, it's probably coming soon.
Oh yeah, I completely agree with you, Jake. I think scalability is definitely a challenge that we have to deal right now. So yeah. Also great. Thanks for the insightful comments there. So following, we're gonna have more specific questions related to the presentations. So we're gonna start with Peng. Thanks for great presentation. So what's the kind of impact of the new vision to customer relying on current generation PyTorch compiler technologies?
Yeah, sorry, my dog wants to join the conversation, so he's sitting next to me. Yeah, so I think PyTorch compilers we have produced many different solutions. As I mentioned in the talk, none of them are completely satisfactory. That's why we have like nth generation of solutions. And we do feel that the current generation address major pain point. And as I also mentioned in the talk, let's not jump the line. So before the new technology is really released and battle tested in the customer, we're still continually supporting the old generation. And the reason we want to show the vision out there is so that for compiler, actually, we're like a core technology. So we actually support other ecosystems, including other people, hardware building on top of our solution. So they need to have a longer time horizon on where we are moving. So we are committed to service the current customers, but at the same time engage with them earlier to figure out what needs to be done if we transition to the new technology. We also want to test if the new technology works or not. So I think a lot of the things would happen organically, but the first principle would be just to make sure customers are happy and the technologies are already solving the problem.
Absolutely, completely agree with you, Peng. But I'm also very excited, to look forward to the kind of upcoming release of the new compiler. Super exciting.
Thank you.
Yeah. Next question is for Yuan. So during your presentation, right, you really talk about training really large models. So I'm curious, how can we optimize those large models for efficient inference cloud, both on cloud and edge?
Yeah, so that's a very good question. So which is again, it's the question we have been laboring on and also struggling on too. And so it's first when we have the very large model, training parameter model is really making it extremely hard to do efficient inferencing. So, and it's of my opinion. So there's many model compression techniques, and so they need to be composed. They need to be multiplicative in order to bring down the models a factor of 1,000 maybe, in order to get to the efficient range of efficient inferencing. And we have quite a bit of experience dealing with these very large models, in particular the OpenAI models. The Copilot model, as my team is actually doing the optimizations for the Copilot model. And it's serving this kind of a large-scale generative model, and is the serving system. Well, I think as Sujoy also mentioned, the serving system is extremely challenging and complex. And yes, we have to think early on, because of typically we build something that is only good for the current generation, and whenever there's some disruptive things coming up, and so there's quite a bit of work to refactoring and trying to understand the bottlenecks, and so some principled thinking is really needed in order to deal with this classical model. And so the second part is moving from cloud to edge, and which is there's a lot of good reasons to move the things to edge, and but there's a lot of interesting problems also related to PyTorch, and how can we get the model out of the PyTorch into the environment of the web browsers, if it's, or on mobile device, and where the Python shouldn't be a dependency, and people, and also move into places like the game engines and all over the places, the Office applications and even the Teams and many places. So that's I think is a very important challenge facing the industry, and hopefully we'll see more systems and more people working on this.
Thank you, Yuan. Yeah, I definitely agree. This is kind of important emerging challenge, right? As we see AI become, much more kind of ubiquitous, right? In our different computing device and modality. Yeah. Thanks, Yuan. Okay, next one. Andrea, you have a great talk, talking about how AWS SageMaker are, kind of doing really large scale training. So I'm curious, how should you, monitor the performance of a really large scale distributed training?
Yes. One of the things that our customers have told us is that doing all the right things to partition a model, use the right tools, the right distribution libraries, the right aggregation, the right primitives, the right collective primitives to aggregate data is really hard. And getting it right is almost impossible at times. You try to do something and it works, but you don't know how fast it's going. So I think there's a need in the industry for a bunch of tools and technologies to help our customers understand, am I training my model efficiently? Am I doing the right things? Am I using all the resources that I'm paying for, that are burning energy, that are costing me money? And so the way we think about it is we have kind of two axes. One is, am I using for instance, all my GPUs effectively? Right? I have all this computational power. Am I doing a good job of that? Am I using all my network effectively? That's kind of axis number one. Axis number two is my model converging as quickly as it should? And if so, what's going wrong? That usually people monitor loss, for instance, right? That's a very common technique. But can I have other insights into how the model is behaving inside so that I can have some early warning, so that I can make some corrections? And so we built, in SageMaker, a debugger to deal with this. So you can look at any tensor inside your model and say, hey, this tensor is going off to a tangent. What's going on? Is my attention working correctly, for instance, in large transformer models? And the other part is we built a profiler that our customers can use to say, hey, how are your resources being used? We have seen customers pay, instantiate 8 GPUs and only use 1. That's more common than I've seen it happen multiple times. And so telling people, hey, are you using all the right primitives here? And you have all this computational power. Are you doing a good job? So I think there is a need to automate all this. These jobs are so big. They're so large. And our customers are training so many models that humans can no longer keep an eye on everything that's going on. And so I think there's a real need to automate all this and turn the training problem into a problem that has into a discipline that has much more parallelism with software development. Profiling is now something that everybody does, and we're trying to lead the charge there. And a lot of it is, it works well with PyTorch, and it's the kind of technology that we're going to be focusing on over the next few years.
Great points, Andrew. Thank you. I completely agree with you that we needed toolings, right, to really kind of automate and be able to really help us really kind of detect any early performance signals for this really large distributed training application. Definitely. Great. Next up, I think this is a question for Jake. Talk about some really interesting applications in AI. I'm curious, how do you handle the training and the serving skew in AI applications using very complex runtime decks?
Training serving skew, is kind of like our big bugaboo that anyone doing, online inference have to handle. Like in batch world, you live the exact same world as training. You train, you do stuff in batch. You're using the exact same code. You just run the forward pass. Everything's simple. Everything's great. You have no training serving skew possible. As soon as you go to streaming, you can kind of make, especially because you're doing kind of mini batches, if you're doing kind of Spark streaming or Flink, you can kind of make them look the same as batch and things still go great. As soon as you go to online, that goes out the window. And even if you've got single simple models, training serving skew becomes tricky, because if you host in, Torch serve or whatever, and you're hosting in some C++ backend, but then at training time, everyone's using the kind of the Python DSL on top of stuff, this can get to be messy. That's just true if you have just single models. Now, if you're going to have a complex DAG, where in this DAG you have fetch a set of candidates from a vector database, join with a SQL database to get some data in, grab some features from a feature store, do inference of one model, output of that goes into inference of another model. At runtime, those are RPC calls out to services. And they think very much in a demand-driven, push out, get response, synchronous process. And so the execution model to do that efficiently is just naturally, just dramatically different than the way you write it when you're writing a training setup. When you write a training DAG, and you imagine writing in your notebook, even if you had a great Python DSL, you'd code up, I'm going to take, load this pandas data frame from this CSV, or from this S3 bucket, or from this HBase table, or whatever. Load this one, and then load that one, and then do some joins and manipulation, run it through some UDF style things, and then, okay, do your forward pass. That process is like very kind of, the data flow feels, there's an inversion of control from push input in, and then it goes blast out and does RPC calls out. So my short answer is, this is like the big scary question when you're doing much more complex DAGs. And I think the real answer is, you need to have the underlying engine behind the scenes be something that's abstracted away from your DSL. And so the same way that, like, in PyTorch and TensorFlow, you've got this kind of language you're writing to describe your graph, and under the hood, there's a whole bunch of other stuff, like C++ stuff that's actually doing the real work. It's, dropping into CUDA and doing all that kind of stuff. For a complex DAG, you also need a DSL that you can describe and run in your notebook, and the underlying engine, when you go out and say, okay, hit compile, I want to serialize that thing down to a thing to serve, needs to be an engine that you can write unit tests around that verify the engine running at runtime via RPC calls out to services, as long as everything doesn't fail and you get the right data, perform exactly the same as your in-memory, inefficient, but fine for exploratory use thing that runs in your notebook. So this is why I kind of like my sort of pitch in my talk is, what we need is a not just open source, but open spec kind of thing, where just as we have, protobufs and thrift and things like that to have a spec between services, we need a spec for inference DAGs, where you can specify something in some simple format that is something we can, gets, and Andrea and team go out and say, okay, we're going to work with Amazon step functions. We're going to make a simple backend step that's implemented in step functions. The folks at any scale will do Ray.io type stuff. Well, they'll have a backend of the same spec in Ray. And similarly, Torch Serve and PyTorch are the same sort of thing, if you're going to have an ensemble of models there. So this is my call out to us in the industry, is it would be really great to kind of collaborate on that, where you can have a kind of spec that you can have different backends that can run in your notebook. Data scientists can play with it, toggle, build a nice complex application. That's not just a single model. You're training an application as an AI-driven application, and they can try it out right there in the notebook, hit compile, and the serialized object is something you can run high performance in some Java-based background, C++-based backend, and you've got unit tests on the framework that runs them that verifies everything done in one is exactly the same as the thing done in the other. You don't have training serving skew because you have tests to show it. Software, not just models.
Thank you, Jake. Super interesting. We actually have a live audience question. We have, it's basically the question is that you have mentioned that as AI applications become more complicated, we need a new breed of open source DAG engine to avoid, bespoke solutions. So do you think is there a risk that the fast pace of AI development that means some of the solutions will soon, to be kind of age out and to be obsolete?
So the kind of thing we built at Salesforce to do our inference DAG is very much a simple agnostic of what the various backends are, kind of plugin based architecture, where you've got an orchestrator that's going to say, you specify your DAG that has dependencies. We'll do a topological sort on who has to happen first and then do other stuff later. and feed the outputs of one several into the others, parallelize when necessary, when you can tell they don't have dependencies. And each node itself is just a plugin that talks to a gRPC backend. That could be whatever. It could be HBase, it could be KF serving, it could be whatever. It could be even talking to a metrics service that's just emitting, just syncing out information to kind of make sure that you're tracking performance related stuff. So I think in the right setup, you don't have to worry about the framework itself, aging out. You swap in, you just write new plugin implementations. We do this at Salesforce right now, where we know that things are changing all the time, and people are like, well, we're going to stop using NVIDIA Triton. We're going to move to Onyx. Great, write another plugin for Orchestrator. Totally irrelevant to us. It's another microservice to stitch into the system. So I don't think that's going to be a huge issue as long as you think about that abstraction early, and you don't say, oh, the right answer is Kubeflow serving. We'll do everything inside of here, and we're baked into this system. And now you're thinking, if you're in the Kubeflow world, Kubeflow is pretty flexible. That might be okay. But if you try to do it with just, Onyx or just there are some setups where you can easily bake yourself into a corner by imagining everything has to be now in Python, and that's exactly how it has to be. That's the standard. But what if in a couple of years we're like, yeah, Python's just kind of too slow for some stuff. It's great for the training time, but at runtime we should use Rust or whatever else it is. You want to make sure that your underlying orchestrator for complex DAGs doesn't care what the backends are. Treat it like microservices do.
Yeah. I agree, definitely. I think as long as you think about using the right software abstraction, right? I think we should not essentially worry too much about particular framework. Yeah, I completely agree. I think we're running kind of short on time, so we're going to close with two more questions. So the next question is for Krishna. So how do you root cause model performance degradation?
Yeah, that's an interesting question, right? So, one of the problems that ML engineers face as we put models into production is that we often don't get labels as quickly as we make predictions, right? So, for example, let's say, we have a churn prediction model that is classifying someone with high risk churn probability, but until the user churns, which could be days, weeks, months out, you really don't get the label, and you don't really know how accurate the model is when you have in production. So there's this. So then, how would you actually figure out whether the model performance is intact or not? So what has emerged in the recent years is this concept of monitoring for data drift that actually gives you a proxy into the model performance. So essentially, what at Fiddler we do is we basically look at the distribution shifts in the input data and the output data, and so you treat the model as a black box. And you look at all the inputs that the model is receiving, and the output it is actually the model score, and you look at the shifts in those distributions. And whenever those distribution shifts are very large, you then alert the ML engineer or the data scientist to look into it. And that's where you get into the root cause analysis, right? For example, there could be real drift, or sometimes it could just be a virtual drift. Being able to sort of separate those two things, real drift could be that something changed, a macroeconomic condition changed, or user behavior has changed for your application. Say, for example, at Facebook, maybe suddenly new kind of users are coming on board or interacting with the product differently. Or virtual drift could be this was basically some sort of data infrastructure issue that the garbage data is being sent, and you may have to go and actually fix the data pipeline, right? So being able to know that root causing that is essentially helpful for you to know whether you need to retrain the model, or like the new data, or do you have to fix your data infrastructure. So that's kind of a good way to think about as you root cause model performance.
Great point. Thank you, Krishna. I think model quality and freshness are super important, right? When we actually build production AI solutions at scale. So yeah, great point. I think we're gonna have our final question of the session. This is for Sujoy. You had a great presentation talking about using simulated data for generated data for simulation. So question: does it matter that objects are floating in the air and or are intersecting with other objects? Does this going to impact the simulation?
So yeah, that's a great question, and I think the answer to that question, of course, it depends. It depends on what your goals are with the model you're training in production. So often we use that as our naive baseline to say, hey, this should work as a initialization for almost any problem. But then you need to start to go and refine that solution to the specific nature of your problem, the specific controlled biases that you want to impose in your problem. So often, like, customers will be working in warehouses. They want warehouse monitoring systems, and they can't collect the data. So they know certain conditions and constraints. So then we start putting those in. But we always want to start with these kinds of wild, crazy nonsense and just see how you do. Because sometimes you'll be surprised at how well you get started, and that gives you a place to iterate from. So does it matter? Yes, but maybe not as much as you think. And the important thing is what aspects of it matter change from application to application. So depending on the problem you're working on, the types of biases or variations really we should say that you're trying to get rid of or add will be specific. And that's also the big thing. That's like why we think we like synthetic data, is it gives you control over that. It's not so much that it solves that problem magically for you, but it gives you control. How do you use that control? Well, because it's free data, as it were, it's good to start from a naive so that you're picking the right dimensions based on information you have, rather than having to say everything up front, go do it, and then hope you're lucky, which is sort of the little advantage we get through the iteration cycles with synthetic data. So the answer is, yeah, you definitely change it in production, but which ways you change it will surprise you.
Right. Fascinating. I think using synthetic data, right, for artificial intelligence, or simulation model training, it definitely provides a lot of unique advantages. Yeah, I definitely expect more and more use case on that. Thank you, Sujoy. And that, I think, concludes our QA session. So I want to thank all the speakers for your wonderful presentations and for sharing really great, insightful comments during our QA session. And also I thank everyone joining our AI at Scale event, and also our QA session. I hope you enjoyed the questions and answers from all the presenters. Just want to quickly reminder, up next we're going to close our event today with a fireside chat between Ian LeCun and Ludovic Hodok from Meta. Hope you can enjoy it. Bye bye.
Thanks.